Again, but they just gave one bar. And then part B of the question says that that bar was connected to a hoop and then wanted the combined moment of inertia of the bar and the hoop together. And then the rest of the problem had to do with the rotational dynamics of that system. So we've seen this kind of question in more recent literature over the last couple of years. This is where I kind of got the problem from. I just did not require that you do the integral calculus part of this problem. And I wanted you to have more than one bar as the spokes of the problem. Now, aside from my mistake, I'm going to treat the problem the way I wanted you to treat the problem, which was the moment of inertia of a bar being 1/12 ml squared about its center, which means for this problem, it's 1/12 m times 2r squared, where the length of the bar would be 2 times the radius of the hoop. And there are 3 bars. So that makes the moment of inertia of the spokes in the problem. Let's see, 2 squared is 4, that's 1/3 times 3, so just mr squared. In addition to that, there's the moment of inertia of the hoop, which is just mr squared, which gives us a combined moment of inertia of the system as 2mr squared. Now, yeah, yours would be different because you wouldn't have had the 2 here, which means your problem would have worked out to be, 1/4 mr squared? Is that right? And then you would have added mr squared to it, so you would have had, instead of 2mr squared, you would have had 5/4 mr squared. So the rest of your problem is going to be slightly different, but it's not a huge modification to the question. On the other hand, what is the mass of the system? By the way, this thing I'm asking right now, I asked it in third period as well, and we were able to come up with the right answer, and then I consistently didn't use it for the rest of the FRQ. So I was getting it wrong the whole time, because even though I called everybody's attention to this and made a big deal about it, I was an idiot. It happens. But the mass of the system is 4m, right? Each bar is massed m, and the hoop is massed m. That's 4 objects, 4m. I'm bringing this up because I think it was Anna Kate and I were doing a tutoring session yesterday morning, and she was asking about one of the questions in my AP. And in that question, one of the objects had a moment of inertia of 9/4 mr squared. I can't remember what it was, but let's say it was that. And she was concerned, and concerned is the wrong word. She was confused because she thought that all moments of inertia had a fraction out front that were less than 1. And I can see how you'd come to that conclusion, because, a hoop, mr squared, a disk, 1/2 mr squared, a hollow sphere is 2/3 mr squared, a solid sphere is 2/5 mr squared, 1/12 ml squared, 1/3 ml squared. They all have this fraction out front that's less than 1. Now, first, this isn't the mass of the, this is not the moment of inertia of the object compared to its mass. That's not what this is. This is a construction of the moment of inertia based on whatever m happens to be. And keep this in mind, this m here is not the mass of the system. Neither was the mass here. The mass of the system is 4m. In fact, if I wanted to write the moment of inertia of the system in terms of the mass of the system, then it would be 1/2 mass of system times r squared. Right, because this m represents the mass of 1 bar or 1 ring. So all of this is still half of the mass of the system, because the mass of the system is 4m. So be careful in these problems when you might be thinking you've done something wrong because your value for the moment of inertia seems out of step with what you would expect. We need to be careful about what m represents in these problems. All All right, does that make sense? A little bit? Whatever. I'm going to move on anyways. I'm getting no tactile, feedback here. I don't know, it's so weird. The Zoom school thing. I'm almost done with the shirt idea, though. I'm so excited about it. I'm sorry, but I'm probably just going to do one shirt. Because I don't know how many people are even going to want a shirt this year. But I've got all sorts of Zoom school stuff on it. And I think it's kind of funny. And I'm going to try and get away with it. But I was thinking that it'd be neat to use the phrase, because I have a, in one part on one side, I have a toilet paper roll that's kind of like acting like a border. So it's got like a little toilet paper in a corner and then toilet paper coming down, and it kind of borders the shirt. So I thought as a cool phrase would be, wiping your mass would be kind of a funny little phrase because of all the wiping jokes that have come up because of toilet paper. And we can't say, obviously wiping your butt, but with the other word, can't say that. But, we could say wiping your mass. It's kind of funny. I thought so, at least. I'm not seeing a lot of laughter out there, but it's definitely funny. And the do's and don'ts of a Zoom meeting, I'm also putting those in there with some things I think are kind of funny too. So, I'm kind of coming up with that, and it's taking a little time. I don't know who's going to want one, but even if nobody makes it or nobody buys one, I'm going to buy one just because it'll be fun. I'll have our names on the back and stuff, so I want to have a shirt. But I don't know how to distribute them. But I don't know. I could put them in bags like outside on my front lawn with everybody's name on them. You just have to come and get your bag. I'll set up like a battleship grid and tell you where yours is on the grid. And then you just go to your grid and get it and walk away. Like picking up a bag of dog poop and you just kind of walk away with it. So anyways, these are the jokes you come here for, right? I'm sure. So dog poop jokes, they top your list of things that you can't wait to hear about in physics class. All right. You know what this is? I just found it on my desk. It's not a dead animal, but it looks like a dead animal. It's just a microphone breath. This is what made me sound like I was huffing and puffing yesterday, like I was out of breath when I got on the roof, because I kept blowing into this, and it wasn't like I intended to, but anyways. I've been told that after 15, 20 minutes, you're supposed to stop everything and let everybody kind of have a breather. This is our breather. You ready to get back to work now? Yeah, you are. Yeah. All right, so you had to find a frictional force. And when I did this problem in third period, and to find a frictional force, I used the fulcrum at the center of mass. But I forgot to hit the record button because I was going to do the fulcrum at the edge for this class. That way people could compare it. So I'll let you take a vote. I don't know what all the yeses are in here. So is this yes, you'd buy a shirt? Or these are leftover yeses for going over the problem? Probably leftover yeses for going over the problem. So here's what I want you to do. Yes, you want me to use the fulcrum at the center. No, you want me to use the fulcrum at the edge. I'll wait patiently. I'm just hoping all those noises are coming out of your speakers and not your headphones, so that your parents in the other room won't be wondering what the heck is going on in physics. Wow, 15 to 10. So it's pretty close. So we're going to do a fulcrum at the center because that's one at 1, but, interesting. Fulcrum at the center, and we can blow through this really quick and see both of them. There's 3 forces that act on the system. If we put the fulcrum at the center, it doesn't change the fact that there's still the gravitational force downwards. There is, and I don't have the, don't actually have the ramp listed there, but let's say the ramp was there. Because the next part, I've been harping on this a little bit. Remember, when you're doing something that's going to involve torque, put the forces at the point of application. That way it's clear where they apply to the object relative to the fulcrum. So if I put the fulcrum there, then the normal force doesn't apply a torque because of the angle with comparison to the fulcrum. And the weight doesn't apply a force because it's located at the fulcrum. So only friction actually is, I'm sorry, I said force, but I meant torque. So only the friction actually applies a torque. So in my net torque equation, the net torque is going to equal I alpha, and I'm going to get friction times radius times the sine of 90 degrees equals I, which we just had, 2mr squared times alpha. Pretty quick. Now, since there were 10 of you who said you wanted to see the fulcrum at the point on the side here, let me just, remind you that that's not a big deal either. If I put the fulcrum there, then my torque is going to be m, not m. I almost made the mistake. 4mg sine theta. Yeah, it's 4m because that's the mass of the objects. Take that third period, I didn't forget. And that's going to times r equals, I has to be 2mr squared plus 4m r squared times alpha. If I move the fulcrum there, I can use the gravitational force as my torque. That's 4mg. See, there's a 4 there. That's 4mg. And r is still my torque arm length, and the sine theta this time is this angle, the angle at which the torque is applied. But I do have to shift my moment of inertia. It's the only difference between these. The problem, though, is that I can't get the frictional force from this. So it doesn't really serve its purpose. It would give me the acceleration rather quickly, but it doesn't give me the frictional force, and we want the frictional force, which is why putting the fulcrum at the center for this case actually benefits us. But to do this problem and get the frictional force, we are going to have to look at the net force on the system. And the net force on this system is, well, there's 4mg sine theta down the ramp minus friction up the ramp equals 4ma. Now, if you actually want to get the answer from this, you're going to have to eliminate acceleration between these two. But only one of them has acceleration. The other one has angular acceleration. So you will have to make a substitution here. And when you make that substitution, I'll remind you, we want to solve this for A. So when I solve this for A, first all the r's cancel, and I'll get that A equals F over 2m. And I'm going to substitute that here. So that I'll get 4mg sine theta minus friction equals, when I substitute in there, I'm going to get 2 times friction, which tells me that the frictional force is going to equal 4mg sine theta divided by 3. Now, yours would be different than this because your moment of inertia was different, but this was the answer I was hoping for. Now, in addition to this, I asked an extra credit question. And by extra credit, I mean that's probably the question that you would be asked at the end of this FRQ that would make the difference between a 4 and a 5. And that is, what minimum coefficient of friction would be necessary for the wheel to roll without slipping? And I think it's an important discussion for us to have. And to have this discussion, I do need to have a little bit clearer workspace. So I'm going to get rid of this on this side to talk about it. Friction is still less than equal to mu times the normal force when we discuss static friction. It's an inequality. We are assuming that generally the frictional force is much less than the maximum. And that's why most objects that roll don't take very much friction, and that's a pretty safe bet. However, keep in mind that there is a minimum. And if we don't have enough friction, our object will not roll. So let's consider what that minimum has to be by keeping our inequality together. So we're going to preserve the inequality and substituting into our friction equation, which is what we talked about first semester. Preserve your inequalities when you can. So I'm going to have for friction 4/3 mg sine theta, which has to be less than equal to mu times normal force, which third period I would have written this wrong, but fourth period I'm not making mistakes like that. 4 mg cosine theta. That's right, third period. I don't make the mistakes again. I mean, I made it three times during third period, so fourth period, no mistakes. Right, Andrew? No mistakes? Just calling you out a little bit. He's terribly quiet. That's good. I will point out the 4mg cancels on both sides. So I get rid of the 4mg there, and I get rid of the 4mg there. If I solve this for mu, I get this interesting thing. It's 1/3 tangent theta. So my object will roll as long as mu is greater than or equal to 1/3 tangent theta. So if I want the minimum coefficient of friction would have to be 1/3 tangent theta. It can be greater than that. That's what the inequality says, but it can't be smaller than this. Now, here's what's interesting. It's got a theta dependence. Now, I want you to hear this clearly. Look, if you have something that's very steep, then stuff doesn't roll, it slides. There's going to be an angle at which you will not be able to stay in contact with your road surface. No matter how sticky your tires are, there are just some angles that don't work. Now, people up north know this. They break friction, and they do it all the time. Because there was a minimum coefficient at the angle of the road. And they've been successful going down that road all year long until there was snow. And then when there's snow, the coefficient changed. It went underneath that minimum for the angle of the road. No amount of snow tires or chains are going to fix that. Florida, luckily, the roads are nice and slick here every time it rains, but we have no hills, really. So you're not really worried about the angle of the road too much, except for all the overpasses, which is why around here when it rains, people slide all over those overpasses, because the angle does get to be sometimes a factor in the minimum required coefficient necessary to stay in contact with the road. Now, I have to end here, not because I want to, but because